Okay, so this is now chapter 2 of our EE124 circuits 2. And chapter 2 will be about power, all about power in AC circuits and the different types of power of AC circuits. Unlike in the electrical circuits 1, we only talk about one type of power. And in DC circuit, that's just power equals the voltage times the current. Here in circuits 2, there are different types of power and definitions for powers. And we will define them all, and we will determine and describe the relationship between them. The first types of power has the instantaneous power. In this circuit, circuit elements produces or consumes power according to the formula. If you remember our formula, the power is just equal to the voltage times the current. In these circuits, this is always true. Now, if we're in AC circuit, because our voltage and current now are not DC, they are alternating, means they're changing over time. So instead of E, we have now a new value for the voltage. And in time domain, we model this value, which will be equal to the maximum value sine of certain angle, omega t. Omega is the angular frequency, and usually it's just omega t when we take the voltage as our reference. But for now, let's just add here an angle. Let's call it theta v. It means the angle or the phase shift of the voltage E, meaning phase shift when you have a sinusoidal signal or source, just like this one. If you have a phase shift, it this one either moves to the right or moves to the left. So they are uh, in shift, and that shift is based from this angle here, theta b. It can be positive, it can be negative, it can be moved to the right or to the left. Let's just call it theta v. For the current, we define it in time domain as similar with the voltage. Instead of em, we have the maximum. Em here is the maximum or the peak value of the voltage because it's a sinusoidal, it's the amplitude. Sine, the same thing, omega t, but this time instead it has a phase shift. Let's call it theta I. So these are the we call them the instantaneous voltage, instantaneous voltage and current in AC circuits. Now, if we define instantaneous power, we will be needing these values, and we will be also using the concept, which is this one. This is the major formulas in electrical engineering. We have actually just two major formulas. We have the Ohm's law. If you know that E is equal to I times R, and power is equal to E times I, and everything much, you can derive those formulas, other formulas for the other parameters based from these formulas. So, for example, here, if we want to determine the instantaneous power, it's the power at a specific time. In circuits 1, we also define there we have a negative and positive power, but it's just the convention, sign convention of the power to state that if the power is positive or the negative, it can be that is the power is being absorbed or the power is being delivered. So here, if it's instantaneous power, so we also, if you observe this, when I'm writing the annotation, if you look at E here, the voltage here is smaller in lower case, while the voltage here in DC, we use uppercase. It means that these voltages are in DC circuits or DC, where it's the average values. While if it's small or lowercase letter, it means it's an instantaneous quantity. So, for example, this one, the power PT, small p in time domain. And if we use the concept, the voltage times the current, then this is just equal to the product also of our instantaneous voltage and the instantaneous current. Then we know that this is our instantaneous voltage. We know that this is our instantaneous current. So if we substitute in our formula, this will be Em times sine omega t plus theta b multiplied by the current Im, also sine omega t plus theta I. So this is the instantaneous power. Then we can rearrange this into, we have Em, Im, then we have sine omega t plus theta v times sine omega t plus theta I. So recall our trigonometric identity before. This is somewhat uh, familiar. We can write this. If you remember, recall one of our identities in trigo. We have, if you multiply two angles, sine, let's say sine u and sine v, where u and v are angles. This is just equal to 1/2 of cosine u minus v, then minus cosine of u plus b. This is an identity. And if you look at here, it's the same, where u is equal to omega t plus theta v, and v is equal to this angle. So if you use that, we can rewrite this now to into Em, Im. That thing now, we can rewrite it into 1/2 times cosine of u minus v. Our u is, this will be our u, and this will be our v. So if we subtract that, because this is u minus v, omega t plus theta v minus omega t plus theta I. So omega t and omega t will cancel out because it's minus. And we have here theta v minus theta I. Then for the second term, minus cosine of the sum of the two. So u plus b, omega t plus omega t is twice omega t. Then plus theta v, then plus theta I. Then if you simplify this, the instantaneous power now will be equal to, we can put this 1/2 here, so it will become Em, Im all over 2. Then we multiply it with cosine of theta v minus theta I, and minus cosine of 2 omega t plus theta b plus theta I. And we can say that this is now our instantaneous power. But usually, we used our voltage as the phase angle of the voltage as our reference. We usually do this. The phase angle of the voltage, theta b, we usually set it to 0 to make it our reference. And we, instead of theta I, let's just call it theta instead of just theta I. And we can substitute this. And also, if you remember, Em, Im, maximum, minimum, maximum and maximum current voltage divided by 2. If you remember the formula for our RMS, VRMS or ERMS, root mean square in circuits 1, this is just equal to the peak value divided by square root of 2. Also for the RMS current, this is also the peak current all over square root of 2. Now, if you multiply the two, what will happen? Square root of 2 times square root of 2. So ERMS times IRMS, this will be EM square root of 2 times IM over square root of 2. So, or this is just EM times IM all over square root of 2 times square root of 2, and that is just equal to 2. So it's the same as our term here. So we can rewrite our power now to be just equal to that one. It's the product of the RMS values, ERMS times IRMS, or we can just write it E and I for convenience, so that you know that these values are in RMS values. In AC circuits, we always do this one. We don't always write RMS, but if you write capital letter or uppercase, it means that those quantities or variables, they are in RMS values. So this will be equal to or multiplied by cosine theta v minus theta I, or theta v is 0, then theta I minus theta I, this is theta. Or we can just, because this is negative, theta v minus theta is actually the angle between the two. So we can also say, instead of theta I here, we can define theta as the angle between, in general, it's the angle between theta v and theta I. So this is the angle between the two. So whatever the angle of theta b, whatever the angle of theta I, if you take the difference, that's always our theta here. Or we call it the angle, base angle. Then minus cosine of 2 omega t plus theta b plus theta I, or just simply plus theta here. And this will be the general equation for the instantaneous power. And if you look at, there are two parts. There are two terms for the instantaneous power. But we don't usually like the instantaneous power, just like the voltage and the current. We want it into a measurable quantity, just like RMS, also the average power here. So the next thing we will be doing is to derive the average power, P average, based from the instantaneous power, just like what we did in solving our average voltage, average current in electrical circuits 1. So if you remember the average theorem, mean average theorem, so we just take the integral of that small p, the instantaneous power. It's a function of time and dt, and we integrate it from 0 to a certain time, which we call capital T, or the period of the sine wave, or the sinusoidal wave. And to take the average, then we divide that with the total 1 over that period. Then we have already our piece of t here. So this is just equal to 1 over t, the integral of ei cosine theta minus cosine of 2 omega t plus theta, then dt from 0 to t. So if you look at this, ei times cosine theta, the first term is just a constant. Well, this one, what will happen to the second part? If you take the integral of this and you take it from 0 to t, then the average value of that, this will become 0 with respect to time, because the average of a cosine wave is always equal to 0. So if you plot the cosine wave, it's like that. So this will always be equal to this area. So they always cancel out. So the average is always equal to 0. So we don't need to take the integral of that. And the only remaining will be ei cosine theta times dt. And we know that cosine ei cosine theta are constant. So we have the integral of, here we have 1 over t, we have e times I cosine theta. So this is a constant. Then the integral of dt is just equal to t. Then we apply our limit from 0 to t. So we have here 1 over, or e times I cosine theta, and over t, then upper limit t minus 0. And t minus 0 is just t, and we have cancelled out that t. And we have the p average now will be equal to e times I cosine of theta. And this will be later on, again, or even if you don't write that as the average, you can just put it P. This is the general formula for the power in AC circuit. And the unit for this is watts. And again, E here is the RMS value for the voltage. I is the RMS value for the current. And we have a new term here. Instead of just multiplying the voltage and the current, we have another term. We call this one the power factor. Power factor. Cosine of theta. Usually denote this one as PF. And this is equal to cosine of that angle, where theta is the angle between the phase angle between the voltage and the current, the E and the I here. And this angle depends also on the triangle impedance. If you remember the triangle impedance, Z. So if you have a Z, Z is equal to R plus J plus or minus JX. So the angle here, you can write this as Z angle theta also. Another formula for the power factor, because if you draw the impedance triangle, if you remember the impedance triangle, this is R, this is Z, and this is X. So if this is that theta. So if you want to determine cosine of theta, so another formula for the power factor, cosine of theta, using trigo functions, K, cosine, adjacent, and hypotenuse. So what is the adjacent side here? The adjacent side is R. So this is R, and the hypotenuse is Z. So another formula for the power factor, PF, is just equal to the quotient or the ratio between the resistance and the impedance. And Z here is this, Z is just equal to the square root of R squared plus X squared. So you can also write this as R all over the square root of R squared plus the reactance X squared. This X can be an inductive reactance. It can be a capacitive reactance. But it doesn't matter if it's negative or positive, because we will always square that one, and the answer will always be positive. So this is our average power and instantaneous power. And also, we will also define this average power into another term. We also call this one average power. Let me write it here. So average power. Instead of calling it average power, we usually name it. This is what we call the active power. Active power. Or true power. Or we also call it the real power. Real power. And we donate it. We use capital P for the notation for the real power. And the unit for the real power is watts. This is in watts. And we can also use other formulas for this. Instead of just EI cosine theta, we can derive other formulas for the average or the real power. This is the actually average power or the real power. This is the power that being absorbed by the resistance in the circuit. So if you want to determine the real power P, we can also use just like what we did in circuits 1. So if you have an impedance here, and you have a current flowing through, you have a voltage here, then the real power of this that being absorbed by this impedance is the power that is being absorbed by the resistance. So if you know the current passing through that, that's just I. You square that and you multiply it with that R here. And that is the real power that is being absorbed by the impedance. If you have impedance here, that's P. So it's also applicable here. But remember that when you are taking this formula, using this formula, you need to remember that the current you need to input in this equation should be the current that is passing through R. Because if it's not, then it's not the real power. We can also use the voltage. The voltage. You square the voltage, you divide it by R. This is also applicable here. But again, this voltage is the voltage across R. In this example, if this is E, the source is, let's say it's this capital E, voltage in RMS, you cannot use this E to solve for the real power. You need to use the voltage across this resistor. So it's better to use I squared R because they are in series. The current flowing through R is the same as the current, total current, and the current through these reactants here. And so this is our first type of power, the real power. And in the next discussion, we will be talking the other types. We have the apparent and the reactive power.